All right, so we're in section 13.3.
Were you in this problem? Yeah.
All right, let's get started. So, one of the basic questions in calculus, kind of one of, if not the main point of calculus, is coming up with a way to describe how functions change. Change is the kind of the central idea of calculus. So we're looking at how a function changes as a variable changes. Well, with multivariable functions, we have more than one variable, so we can have things changing in more ways than one. So we have to come up with this idea of a partial derivative, and we get to learn our first new symbol this year. So we're going to define what we mean by a partial derivative. So today we're going to talk about the first partial derivative. Of a function z equals f of xy. So this is, we're going to come up with this definition. There are several ways that we write this. So we're going to say that the first partial derivative and we're going to say with respect to x, and we write this as written as f sub x. We can also put our functional dependence in there, f sub x of x, y. We can write z sub x. All of these mean the same thing. And here's our new symbol. We have this curly d. d dx of f of xy. We can write dz dx.
A curly Z.
Oh. So our d is curvy. Our d is curvy. Both. So as opposed to a d that looks like this, we write it curvy.
So then the lowercase deltas?
So not exactly, because the lowercase delta is this.
Okay.
So it's just a curvy d.
Okay.
All of these things we note our notation for the first partial derivative with respect to x of this function. So the curvy d just means we're taking is to remind us that we're taking the derivative with respect to x. So all of these symbols denote the same thing, and our definition, all of these equal the limit as delta x approaches 0 of f sub x plus delta x comma y minus f of xy, just like we would expect over delta x. So what we're doing here is taking the derivative of our function with respect to x and considering y a constant. So we hold y, we consider y, we treat y as a constant is what we're doing here. And we can do the same thing with respect to y. So our first partial with respect to y we're going to write f sub y, same list of symbols, f sub y of x and y, z sub y, d dy of f of xy, dz dy, or df dy. All of these mean the same thing. Our definition is this is the limit as delta y approaches 0 of f of x comma y plus delta y. So we're just letting y change minus f of xy over delta y. And again, when we take this derivative, we're treating x as a constant. So when we take the derivative with respect to x, we treat y as a constant. When we take the derivative with respect to y, we treat x as a constant. So we're just doing all the normal things that we do with derivatives. We just have, when we have these multivariable functions, we treat one of the variables as a constant when we take our derivative. So that's our definition. We say that the derivative, the partial derivative, exists when this limit exists. Oh, thank you. There we go. So, questions about our definition? Standard definition of a derivative. We're just treating one of our variables, one or the other of the variables, as a constant. All right, when we evaluate our derivative at a point, just again some more notation. So when we evaluate our derivative at a point, we'll say x0, y0. Our notation is df, for example, if we're evaluating the partial with respect to x, our notation is, we could write this. We could say this is f sub x at x0, y0. And we could, if we're taking our partial with respect to y, and that's the same as saying f sub y at x0, y0. So those are two different notations for evaluating our partial derivative at a point. And again, to find our partial with respect to x, we hold y constant. To find our partial with respect to y, we hold x constant. And what we're doing just visually, graphically, if we look, let me sketch a couple of surfaces here, just to show graphically what we're looking at with partial derivatives, and then we'll practice taking some partial derivatives. It's not difficult. But this is going to lead us into some very interesting ideas. So we have some surface up here above the xy plane. When we are taking the partial with respect to x, we're picking some constant value of y, and we are looking at how the surface changes with that constant value of y. So let's say this curve represents this constant value of y down here. If I project this down onto the plane, we have y equals y0 along that line. So we're holding y constant, and f sub x The derivative with respect to x gives the slope of this curve at a particular point. So we're holding y constant. The partial with respect to x tells us how, gives us the slope of this curve with y constant. So it's telling us how the surface changes when we hold y at this particular value. And we do the same thing over here. Here's our surface up above the plane. And for this one, we're holding x at a constant value. So there's the curve on the surface for a particular value of x. Project this down into the plane. And here we have this constant value of x. That's x equals x0. And f sub y gives the slope of this curve. So we're holding x constant, and we're seeing how our function changes as y varies. So graphically, this is what we're looking at with partial derivatives. Is that all making sense? So the first thing I want to do is practice a little bit visualizing some partial derivatives. So in your book on page 912. Yes. Okay. Let's look at, we'll do a couple of examples here where we're doing some calculation. We have h of xy equals x squared minus y squared. And we want to find the slope in the x and y direction at the point negative 2, 1, 3. So we want to find the slope in x and y direction. So first off, before we find our slope, what kind of surface does this describe? Z equals x squared minus y squared. I heard a hyperbola, a cylinder. What did you say, Liam? A saddle, there we go. If we think of this as z equals x squared minus y squared, if y equals 0, we have a parabola. If x equals 0, we have a parabola. If z is a constant, we have hyperbolas. So we have a combination of hyperbolas and parabolas. So that's going to be a hyperbolic paraboloid, a saddle shape. That looks like number 49, something like number 49 that we just looked at. So this is a hyperbolic paraboloid. So the slope in the x and y direction, the slope in the x direction, as x changes but y is constant, that's our partial with respect to x. So we're going to say the partial with respect to x of h of xy. What's going to be our partial with respect to x? It's 2x. And we'll do the partial, because we're going to have to do it anyway. The partial with respect to y of our function is just minus 2y. And then at our points, we can plug in our points at negative 2, 1, 3. We're just plugging in that point. We have h sub x of xy. I'm using the notation interchangeably here. We just get negative 4. And at our point here, we're just plugging in our point here, h sub y of xy is negative 2. So at this point, the slope with respect to x, we're going downhill in the x direction. We'd be going downhill in the y direction on that surface. Let's look at another example. We'll just calculate. We'll just calculate our partial derivatives. We want to evaluate it at a point. Let's say z equals the cosine of 2x minus y, and we want our first partials with respect to x and with respect to y. So dz dx is going to equal what here? Negative 2 sine 2x minus y. And the partial with respect to y? Sine, negative sine, positive, negative, positive. Right, we get a negative from the derivative of the cosine, we get a negative from the derivative of minus y. So we just get sine of 2x minus y. So we just treat our other variable as a constant, take derivatives just like we normally do. All right, let's do one a little more, that requires a little more thought, and then we will be done. What we're going to talk about as we go on with partial derivatives, yeah, Liam.
Sorry, how did you draw the negative 2?
Here we're taking the partial with respect to y.
Oh.
So we take.
Okay, but.
Yeah, no, here.
Yeah, I didn't see that.
Yeah, we still have the negative 2 here, but we don't end up with a negative sign there because we get the negative sign from there as well. Okay. So we end up where we're going with this partial derivatives. We're going to talk about higher order partial derivatives. So first partials, second partials, third partials. What happens with the higher order partial derivatives is we can take the partial with respect to x, and then take the partial with respect to y, take the partial with respect to x, and then take the partial with respect to x again. So we get all kinds of higher order partial derivatives. And then we have, because of the different variables involved, we have several different kinds of chain rules that are involved with partial derivatives. So leads us into some interesting ideas. All right, so let's say for this example we have f of xy equals 3x cubed minus 12xy plus y cubed. And we want to find where f sub x and f sub y equals 0 simultaneously. So we want to find where both of our first partials equal 0 at the same time. So before we do that, what do you think this would represent on the surface? So Katie says flat, Griff says a maximum or minimum. So it turns out that you're both kind of on the right track. If our first partials are 0 simultaneously, we end up with a maximum or a minimum. So yeah, like a tangent. So we end up talking about tangent planes at maximums and minimums rather than tangent lines. All right. So, and we'll talk more about this idea later when we talk about maximizing and minimizing multivariable functions. Again, leads into a lot of interesting ideas. All right, so we want our first partial with respect to x, f sub x. What's going to be our partial of this function with respect to x? 9x squared minus 12y, and that's it. Y cubed is just constant. Derivative of a constant is 0. So f sub y, partial with respect to y, is going to be minus 12x plus 3y squared. This whole first term is a constant, so the derivative of a constant is 0, so we don't have to worry about that. And we want these equal to 0 simultaneously. So we have two equations, two unknowns. So we're going to say 9x squared minus 12y equals 0. So I'm going to say that solving this for x, I'm going to say 3x squared equals 4y. And for this one, I get 3y squared equals 12x from this equation. And I can say y squared equals 4x, so x equals y squared over 4. Now I'm going to substitute back into this equation. And I get, substituting for x in here, I get 3 times y squared over 4 squared equals 4y. And I need to work on this a little bit. When I simplify this, I end up with 3y to the 4th minus 64y equals 0. I can factor this and solve, and I end up with x equals 0. Sorry, y equals 0. Got ahead of myself. Or y equals 4 over 3 to the 1/3. So I just factor out a y, and I can solve for y. Substitute back into my equation, and I get x equals 0, or x equals 4 over 3 to the 2/3. So our points are 0, 0, and 4 over 3 to the 2/3, comma, 4 over 3 to the 1/3. So we're going to have a maximum or a minimum at 0, 0, and at these 2 points. Make sense? So first partials, the idea is not difficult. Usually with the functions it's not difficult. Where things start getting interesting is when we start taking mixed partials, when we start maximizing or minimizing functions, and we find some different ways of doing that, and when we start talking about chain rules. And where we're going with these partial derivatives, we're going to tie it back into vectors. We're going to find a vector function that represents the direction of the maximum rate of change on our surface. And that's called the gradient. So we end up with using partial derivatives to find this gradient function. And gradients also turn out to be normal vectors to surfaces. So we find this vector function with partial derivatives that end up giving us vector information about curves and surfaces. That's kind of the direction we're going to tie it back in with vectors. But in the meantime, we'll talk about maximizing, minimizing multivariable functions, finding maximum and minima on surfaces, and some other topics involving partial derivatives. So any questions? Yes?
How did you get -64?
Let's see. Yeah, so we get a 16 here from the, okay, yeah.
In the homework there are problems with like f of x, y, and z. Can you find it so that you
Yeah, if you have functions of more than 2 variables, it's the exact same thing. You take the derivative with respect to one variable and hold all the rest of the other variables constant. And we can do that with as many, we could add as many variables as we want. So partial with respect to x, take the derivative with respect to x, all the other variables are constant. All right, homework. Oh, we don't get very many like this, do we? All right, there you go.